Hi, this is Patrick here on behalf of Group B6, and I'm going to explain the entity relationship diagram. It consists of four external entities of a doctor, BSL value, patient, and prescription. Now, the doctor enters BSL values where the relationship is 1 to many. Patient has BSL values where the relationship is 1 to many. Now, the patient receives prescription, and that again is 1 to many. And doctor prescribes prescription, that is a many-to-many relationship. Now the doctor has a primary key of doctor ID with the attributes of name, designation, contact information, and verification. The BSL values have attributes of BSL ID, insulin dosage, and insulin type. The patient has attributes of patient ID, age, gender, and address, where patient ID is a primary key. And in the BSL value, BSL ID is a primary key. In prescription, it has attributes of prescription ID, patient ID, medication name, medication dosage, medication time, and doctor name, where prescription ID is the primary key.
The part of our system using data is predominantly the prescription entity. When the prescription is made, a number of input data is used, including blood sugar levels and patient information such as their UR, name, and date of birth, all of which are included on the prescription and on their labels. The prescription entity uses data such as patient ID, script ID, medication name, the required dosage, and the time medication is administered to the patient. Some issues faced when designing data stores were that prescriptions were being duplicated when being stored. To combat this issue, we have now implemented a unique identifier for every prescription to avoid the duplication of scripts. All scripts will also be linked back to the Kilbundura Hospital patient UR. Also, previously, older recorded BSL values were being overwritten every time a new one was recorded. This meant that the clinicians were unable to refer to older BSLs and was also causing medico-legal issues for Kilbundura Hospital. Functional interoperability refers to the ability to exchange information between programs. Semantic interoperability refers to the ability for both programs to understand the information being sent. To help enable and facilitate interoperability and information exchange between our system with the PMI, it would be ideal that the e-prescription system operates using the HL7 messaging system so that the functional interoperability of exchanging information from the PMI and the e-prescription system is at an optimum. HL7 dictates the communication format that most information is communicated in via the PMI. It is also the type of messaging used with existing e-health technologies. This means that only certain terminology will be able to enter and accepted into the e-prescription system and may add constraints to the designers involved in creating the system and affect the way that information entered into the system in order for it to work efficiently and interoperably. The screen displayed currently on screen is an example of the pharmacist view of our proposed system. Within this screenshot, you can see that all relevant players are identified. This includes the patient, pharmacist, doctor, and their contact details. Data inputs are grayed out for pharmacist login, as the pharmacist doesn't have the authority to change any of the inputs. Inputs are separated to a level that ensures all information is accurate. As you can see, the strength of the dose, the measurement, and the frequency are each displayed separately to avoid any errors. This ensures that information such as the unit of drug are put in accurately. The screen design developed for our e-prescription system ensures data quality by achieving the following: providing a simple and easy to navigate design that helps facilitate transparency. The interface is simple and easy to use and easy to navigate. It contains clearly labelled controls, buttons, and icons. Unavailable commands are grayed out to indicate they cannot be changed. Contact information is included, such as the telephone extension of the prescriber, so the pharmacist can contact before sending any queries. When a user-entered command contains errors, the program will highlight erroneous parts and allow the user to make a correction without retyping the entire command. Our screen will also have inbuilt rules that enforce data integrity. For example, a pharmacist is unable to change any of the information regarding drug, dosage, BSL, and insulin type. However, they are able to send a query to the prescriber or doctor if they believe that this information is incorrect, contraindicated, or inappropriate.
Thank you.